So theorem 3.24 is what's called Cauchy and Schwarz inequality. Again, this is a very helpful inequality if you do calculations with vectors. And please, can you mute yourself? Okay. So Cauchy and Schwarz are just two names of mathematicians, and in Russia you would call it Cauchy, Schwarz, and Bunyakovsky. So there would be another name. Yeah. So apparently that's an important inequality if so many people are mentioned in the name. But for us, at least in our setting, the inequality is very simple. So here we have u and v, two vectors in Rn. And then the Cauchy-Schwarz inequality essentially allows us to estimate the dot product. So u dot v dot product is the absolute value of norm u times norm v times cosine theta. And now absolute value can be distributed. Absolute value of a positive number is just the positive number. Absolute value of v is just, again, absolute value of v because of the positive number. Then we have the absolute value of cosine theta. And what is the largest value of cosine? How big can cosine be at most?
1.
1. So it turns out this is smaller than norm u times norm v. So this here, norm u times v, absolute value is smaller or equal to norm u times norm v. Sorry. This smaller than this, smaller or equal, is what's called the Cauchy-Schwarz inequality. Very easy. Here, it turns out this is not only true for the Euclidean dot product, which we just saw. This is more general, and that's actually why it's so famous. So this is always true if we have an inner product, and then suddenly the other products have no cosine anymore, but it's still true. So that's actually why it's such a big thing. But okay, so for us, in our special case, that's very easy to see. Absolute value of u dot v is smaller or equal to norm u times norm v. So then we will also use this right away. And like I said, now the next 3 results are kind of geometry results. So theorem 3.25 has actually 2 parts to it. So here, part A, here we have u, v in Rn. And the picture here, this time I should be smarter and do it like this. So this is u, this is v, then this is u plus v. So we have a triangle. And then this side of the triangle is shorter than the sum of the 2 other sides of the triangle. So when we have u plus v smaller than norm u plus norm v. And because it means in a triangle, one side is always shorter than the sum of the 2 other sides. And it doesn't matter which side you pick. No? And for this reason, this is called the triangle inequality. Now you can use the same pictures, and instead of just looking at the vectors, you make every endpoint a point. And every endpoint you give a name. So part B, if you have A, B, C, 3 points in Rn. So I make the same picture again. But instead of giving names to the vectors, I call these points A, B, and C. Maybe I should better call it the other way, so it's more easy to understand. So then the distance from A to B is shorter than the distance from A to C plus the distance from C to B. So it matches this up here. So then the distance from A to B is always smaller or equal to the distance from A to C plus the distance from C to B. that essentially means no matter which detour you take, it's always longer. No? But it's the same statement. So if you know this right away because you see it's the same picture and you would show it in the same way. And I just like to show part A. And you see here right away an application of the Cauchy-Schwarz inequality. That's why this is so nice here. So we start with the left-hand side, but we will square it. So we can connect, once we square it, we can connect the norm to the dot product easier. So we do norm u plus v squared is u plus v dot u plus v. So yeah, also remember, without the square, I have to have the square root. When I square it, the square root disappears. So now we can here distribute. So this is u dot u plus u dot v plus v dot u plus v dot v. The first thing is now that u dot v and v dot u is the same because our dot product is symmetric. So it turns out this is u dot u plus 2 times u dot v plus v dot v. Now we know by Cauchy-Schwarz u dot v, the absolute value, so this can be plus or minus, but even if I take it always plus, it's smaller than u times v norm. So now we use this result here, 3.24. This is smaller than u dot u plus 2 times norm u times norm v, that's from here, plus v times v. Last thing, u dot u is norm u squared, v dot v is norm v squared. And now we see, oh, this is just a perfect square. Yeah, so we have this group smaller or equal to this. So therefore, norm u plus v squared smaller or equal to norm u plus norm v squared. So that's what we have shown here. And now we can take the square root on both sides. Square root is a monotone increasing function, so square root respects inequality, so it doesn't change inequalities. So when I take square root on both sides, it follows norm u plus v smaller or equal norm u plus norm v. And that's exactly what we like to show. So this is one geometrical result. And there are 2 more in the book. I just like to write them down. The first one, again, with a picture, so you see what it actually means. And you would do it very similar. You translate every time a length in a dot product and just multiply it out and simplify. So this is how you do the next 2. And I just like to write them down. And then this finishes our section 3.2. So I just like to do 2 more. So the next one is what's called theorem 3.26. So here we have again u and v in Rn. So this time, let's say here, this is u, this is v. Then I put v also here, and then this here is also u. Then this here, this diagonal is u plus v, and this diagonal is u minus v. So one diagonal is u plus v, one diagonal is u minus v. And now this theorem is called the parallelogram equality. So it turns out when you take the sum of the 2 diagonals, you take the length of this squared and the length of this squared, you get just the sum of the squares of all sides. So 2 because u is twice and v is twice. Yeah. And how do you do this? You write this with a dot product, this with a dot product, and just multiply out, and you get it. So it turns out the dot product is a very nice way of sometimes, doesn't work all the time, but if the dot product works, it's a very nice way of proving geometrical results. So this is called the parallelogram equality. So in a parallelogram, the sum of the squares of the diagonals is equal to the sum of the squares of each side. Okay, and then finally, we have theorem 3.27. That looks first a little bit strange. But again, if you like to show why this is actually true, you just plug in dot product and comes out magically. So it turns out u dot v is one quarter of u plus v squared minus norm u minus v squared. So this is sometimes called the spectral equality. So what is special about this? So this is special because, remember, we can calculate the norm with the help of the dot product. So let's say if you have implemented a computer program which can calculate the dot product, you can automatically calculate the norm. This one now goes in the other direction. If you have a computer program which can calculate a norm, you can automatically also calculate the dot product. So you can go back and forth. You can either do dot products or norms. So this is kind of why this theorem, why anyone thought this is important. It means with the help of the norm, if you are able to calculate norms, for example, with a computer or with any other device, you can also automatically calculate dot products. So this relates, yeah?
I'm sorry, Professor, does that say 1/4?
Yes, 1/4.
Okay, thank you.
And if you multiply it out, you always have this mixed term, u times v, v times u. You have 2 from here, 2 from here. So it adds up to 4 of them. And then by 1/4, you get u times v. No? Also again, I don't like to show the calculation, but here you put a dot product, here you put a dot product. It gets lengthy. And at the end, everything cancels and only u times v is left over. Okay, so I would like to leave it like this. If I would have more time, I would go over the proof. But as I said, it's really just plugging in the dot products. So what I will do now is, okay, first, are there any more questions? Let's start first with the lecture from today. Anything about the content we did today? Also again, the points were norm, distance, dot product. So these are the 3 big topics from this class today, plus some geometrical results. And then on Monday, we continue about the special things if 2 vectors are perpendicular. And you can already imagine Pythagoras theorem will come up there. And yeah, so that will be on Monday then in section, I think it's 3.3, before we go to the cross product in 3.5. So what I will do then, if there are no more questions, I stop sharing the screen. I cancel the meeting. I stop the meeting because I have to save my video from now. And then around 5 minutes before 10:30, I send out another link. And then this is the link for the practice quiz. So then please log in with a phone on Zoom. And position the phone that I can essentially see you, like how you work on your exam, like you would do in a classroom, and turn on your computer. So by email, I will send you the PDF file with your quiz questions. And there will be 3 quiz questions. I don't think you really need 40 minutes, but that's not the point. The point is that today we practice that you write your solutions on paper, scan your solution, and when I say time is up, you scan it and send it to me by PDF.
Professor, how many sheets of paper should we grab?
I would say 3 to 4, but yeah, just make sure put a few more there.
Okay.
Yeah.
I have a question as well.
Yes.
Are we supposed to scan like with Zoom open, obviously, right? But like
no, yeah. So you write the exam with Zoom open, no?
Yeah.
once you're finished, you say, I'm finished. And I say, okay, go ahead. Then you turn off Zoom, scan it, and send it to me.
Okay.
Mm-hmm. And that has worked in Spring for me. And I would, if there's nothing what happens, I would say I would like to do the same thing now. I don't like to use lockdown. I mean, for sure, I heard that some people use lockdown browser on the computer. Yeah, for me, that's fine. I see you when you take the exam, and I hope that's good enough.
If we have a scanner, are we allowed to just take our
Then
Zoom?
just let me know.
Okay.
Then just tell me I'm done, and I go to my scanner and scan it now, and then that's fine too, no? Any other questions?
Professor, so do we tell you when we're done or just go and scan it?
Maybe you can just raise your hand and say, I'm scanning now, no? And then,
Okay, I'll do it.
So I know what you're doing, no?
Okay.
Yeah. Okay, if everything is okay, I've quit the meeting now. And then around in 20 minutes, actually 15 minutes, you get another email with a new link for Zoom, which you then use with your phone.
Professor?
Yeah?
So do we have like a deadline for to submit the exam? Because when I scan a paper, it takes like a couple minutes.
That's fine. So if it takes 5 minutes, it takes 5 minutes. Don't worry.
Okay.
I noticed already in spring, some students take 2 minutes, some students take 7 minutes. I don't mind. Yeah.
Okay, thank you.
Mm-hmm. Okay, I would like to stop so I can actually save my video now. And as I said, in a few minutes, also 15 minutes, maybe you get a new link by mail. No?
Thank you.
Okay, see you in a few minutes.